Okay, this will be our final heat exchange example problem, but because it is a little bit longer and it involves more algebra, I wanted to kind of separate it out from the other heat exchange problems from the last video, right? You'll find this example on slide 4 of your chapter 5 PowerPoint, but now we're past the silver part and you'll see at the bottom there's some information about a heat exchange that occurs between a heated chunk of nickel and water, okay? And so what I've done is I've read that problem and I recommend you do the same thing and I've made a list of information, all right? There's a heat exchange going on and I'm given information about water, right? And water's inside a calorimeter, but you don't really have to worry about the calorimeter because the types of problems that we're going to enact this semester will only be heat exchange between two different things. So you can kind of ignore the last sentence of this problem, don't really worry about it. Everything that we need, all right, to do this problem and the way that we're doing it this semester will be found in everything before that last sentence. So I made a list. I was given that I had 150.0 grams of water. I was given a heat capacity of water. I was told that water was initially at 23.5 degrees Celsius and water was observed to have 25.0 degrees Celsius as its final temperature. I make that list, labeling, all right, units, right, and variables, and paying attention to significant figures along the way. The same thing can be done with nickel. There's also information about nickel. Now, we don't know its mass, and in fact, that's the whole point of the problem. But what we are given, right, is its heat capacity and its initial temperature. So nickel is this hot object. We dump it into something colder, and what we see is a final temperature is reached. Now, we aren't given a final temperature of nickel, but we do know that we have it, okay? So even though we aren't given it directly, we do know that heat exchanges occur, right, until all final temperatures are the same. So even though we're not explicitly given this and it looks like another unknown, well, hold on a second. If the final temperature of water is 25 degrees Celsius, then the final temperature of nickel must be the same. Otherwise, heat would keep flowing between the two objects, okay, until they equal out. So if I know the final temperature of one thing, you know the final temperature of everything in terms of a heat exchange, right? Because you'll always get to that final point. The heat exchange will always be done, okay? So actually, I just have this one unknown. All right, so how do I even set this up? It's just a big list of information right now. Well, are more than one objects mentioned? Yeah. Is one object hotter than the other one? Are they going to exchange heat? Absolutely. So you know then that your starting point is minus Q lost equals Q gained. Right? All right, so that helps out. So then let's take the next step. What's losing heat in this scenario? Well, nickel's hot, so it must be losing heat. And where's that heat going? Well, heat flows from hot to cold. All right, nickel's hotter than water initially, so it goes into the colder water. So now, remember, we have this list written down. I'm going to keep working, but I have to move up here on my board. Okay. What am I going to substitute in for Q of nickel? Right. Well, what am I given about nickel that tells me or gives me a pathway? What am I given about nickel that gives me a pathway towards calculating a Q? Well, I'm given a specific heat. So just like other problems, if I'm given a specific heat, what can I do for Q of nickel? On this side of my work, I can remember my minus sign out in front. And, oh, that C that's given for nickel, it has a grams in the denominator. So I can write this as minus the mass of nickel, C of nickel, T final minus T initial of nickel. Essentially, I can use Q equals MC delta T. If Q equals MC delta T, then negative Q looks like negative MC delta T. Okay. I could do the same thing with water. What information about water am I given that tells me, all right, how to calculate its Q? I'm given a specific heat. So I know that Q equals MC delta T, all right, when I'm given a C that has a grams in the denominator. So essentially I have this equation now that has 1, 2, 3, 4, 5, 6, 7, 8 unknowns in it. And notice how I've organized things. I have this list, and I want to make sure the correct numbers get in the same spots. So on one side, I've used labels of H2O to remind myself that I'm talking about H2O. And on the other side, I've used labels of nickel to remind myself that I got to put the correct number in the correct spot to get the correct answer. Now, if you go back and look at our list, do we know C of nickel? Yes. Do we have an initial and final temperature in our list? Absolutely. Same thing with the mass of water. C of water, T final, T initial of water. We have everything, and the only unknown is the mass of nickel. And that's actually what we're asked to calculate. So that is great news, because now I can go ahead and substitute in numbers, pay attention to significant figures and units, and solve for this variable. Solve for it like it was an x in an algebra problem, because that's exactly what this is. So I remember my minus sign. Now I'm going to get lazy, and I'm going to know my M is my mass of nickel. Okay, so I'm going to just call that M. My heat capacity of nickel was 0.444 joules per gram degrees Celsius, right? My final temperature of nickel was 25.0 degrees Celsius, and my initial temperature of nickel was the 99.8 degrees Celsius. Right. On the other side of my equation, I'm running out of room here, so I'm going to bring this part down here, right? Do I have a mass of water? Yep, 150.0 grams of water. 4.184 joules per gram degrees Celsius. Water has the same TF, 25.0 degrees Celsius, but it had a different TI, 23.5 degrees Celsius. So now we see how it's just algebra. We can go ahead and we can start to cancel things, combine terms. We follow our algebra steps, okay? And we see that we have parentheses here. So the way that I do this, and because it's an algebra problem, there are many, many, many ways of doing this. I'm going to show you one way. I was going to pay attention to our order of operations, and I'm going to do the things in the parentheses first, okay? So what I do here is I take this, and what I'll get out for this math right here is I'll actually get out minus 74, oh, sorry, I wrote that terribly. I'll get out minus 74.8, right, for that work in parentheses, right? And here what we're going to get out is we're going to get out positive 1.5 degrees Celsius. So if I go and I take this, the negative and the negative on this side, they cancel. And I get mass times 0.444 joules per gram degrees Celsius is now multiplying 74.8 degrees Celsius. So one more time, I took this negative here after I did the subtraction, combine it with the negative out front, and now this is positive, right? On this side, I have, all right, 150.0 grams. I'm actually going to multiply these together, right? The grams and the grams are going to cancel. And what I'll be left with on this side is 627.6, right? Let's pay attention to significant figures. They would all be significant figures, right? Joules per degree Celsius times 1.5 degrees Celsius. Okay? Degrees Celsius here and degrees Celsius here are going to cancel. Let's do the next step over here. I have some numbers. So let's go ahead and let's multiply these together. So what I'm going to get over here is mass times 33.2112. Let's pay attention to significant figures, right? Let's pay attention to units, and I kind of brought them outside this parentheses. Joules, right, per gram, right, are going to be equal to, okay, let's multiply these two things together. And what do we notice happens here? Degrees Celsius cancel with degrees Celsius. So what we'll get on this side is 941.4 joules. Now we're only going to have 2 degrees Celsius, two significant figures on this side. Notice when I did this subtraction step, this number is good to this decimal place, this number is good to this decimal place. So we end up with 2 significant figures here. That carries down there. And significant figures are some of the hardest things to keep track of in these problems because there's not only multiplication steps, there's also subtraction steps. But that's why I kind of wanted to do this example separately and in full So to remind you of all those different skills we've been developing in terms of mathematical manipulations and how they apply in this scenario as well. So how do I solve for mass? What's the last thing that we do? Well, we take all of this and we divide over to this side. Now notice what's going to happen. Joules is going to cancel with joules. I'm going to divide by 1 over grams. 1 over grams, right? When I divide by this, becomes grams, okay? So if we take this 33.2112, right? 1 over grams, right? And we do this math, well, 1 over grams just gives me grams as my answer, okay? So we would do this division on both sides, just to kind of realize where this is happening or how this is occurring, all right? Once the joules cancel. And then we'll isolate mass. And that last algebraic step leads us to a mass that is equal to 28.34586 grams. But I've paid attention to significant figures, and that final step involved a division. And notice I only rounded now that we're at the end, okay? That final step involved a division between a number that had 2 significant figures and another number that had 3 significant figures, right? So using my correct rounding rules, my final answer is 28 grams. So this is the most involved type of problem, but you have the algebra skills to do it, so please do not be intimidated by this. I know that you can do it. It's just about staying organized as always, units and significant figure, not messing with, or mixing up, I should say, not mixing up the multiplication, division rules with the addition, subtraction rules. It's a multi-step algebra problem where you keep significant figures along the way. Let's make sense of our answer. If we would ever get a negative mass, that's wrong, okay? So we have a mass that's positive. So at least that kind of indicates that I probably didn't make a sign error along the way. If you do get a negative mass, that's what you go look for. You go back and you say, hey, did I remember that minus sign on one side of my heat exchange? Did I remember negative signs when I did my delta T's, okay? You go and you look for a sign error, okay? The temperatures made sense. Sometimes you have to solve for these temperatures. And we had an object that was at 23.5 degrees Celsius and one that was hotter. What's the final temperature? Somewhere in between. That kind of makes sense, okay? All right. If you ever try to solve for a heat capacities are always positive, okay? So again, if you end up with a negative heat capacity at the end of one of these problems, go and check your work, look for a sign error, okay? But like I keep saying, have some confidence, don't be intimidated. If you understand this example, then you'll be able to do, with practice, any homework problem that I give and any problem from Chem 101, right? We have 2 more topics in this chapter to talk about, okay? But they're a little bit easier to digest. So this is kind of the big hurdle in this chapter. So once you get comfortable with calorimeter problems, again, establish some confidence in yourself that you'll be able to handle any scenario that you'll see in this chapter. And next time we're actually going to talk about something that hopefully you're familiar with, but if not, I'm going to treat it like you've never seen it before. We're going to talk about Hess's law next.